Good afternoon. The title of the talk, A Planet for Goldilocks. We are looking for planets that could harbor life. In fact, government agencies, both here and abroad, are committed to finding evidence of life beyond Earth and are investing a lot of resources towards that objective. So I'm going to tell you about one pathway, one possible pathway towards that objective, which is finding evidence of life on exoplanets, planets orbiting stars beyond Earth. And this is largely born out of the progress that the Kepler mission has made over the last 5 years. Kepler is a space telescope that was launched in 2009. It's still up there, it's still taking data, but its level 1 science requirements are almost completing. So I'll tell you about that and how it's changing the landscape of this search. There are actually 3 pathways for finding evidence of life beyond Earth. 2 of them are symbolized here through these images. So on the left, we've got an image of the geysers erupting from the subsurface of Enceladus, one of the outer moons in the solar system. And so it represents our search for life in the solar system. Right now, we have no indication that there is other life in the solar system, but it could be lurking in this subsurface ocean on the satellites of Enceladus in Europa. It could be lurking on subsurface Mars someplace, maybe in a subsurface cave or some niche on Mars. Maybe we will go to Mars and we won't find life. Maybe we'll find death in the form of fossils. But that in and of itself is going to be very interesting because until now we've only got this one unique tree of life in all its particularities. And we want to know if that kind of a tree of life is ubiquitous in the universe or if it's diverse. The other image represents a radio telescope and the idea that you can listen for signals in the universe, perhaps signals that are not astrophysical in origin. That is, they cannot be explained by any astrophysical body that we know of in the universe, and therefore perhaps are an indication of some kind of technology that exists out in the galaxy. And so this is the famous SETI searches. SETI stands for Search for Extraterrestrial Intelligence. We have a SETI Institute here as our neighbor in Mountain View, but there are many different SETI organizations. There's a SETI at Berkeley, at Harvard. They're scattered all over the world. And this got a recent boon by an investment from the private sector. Yuri Milner up the hill has invested or committed to investing a sizable amount of money to rent the Green Bank telescope to do this kind of search for life. But the third pathway for finding evidence of life emerged about 20 years ago. I was a graduate student at the time, and I happened to be invited to go to a conference in Florence, Italy, because my advisor built this instrument that was operating on the Keck 10-meter telescope in Hawaii. And it was there at this conference in 1995 when a Swiss astronomer, Michel Mayor, announced the discovery of the first planet orbiting a normal star, kind of like our sun. And here's an artist's rendering of it. It's not an actual image. Everything you see is going to be an artist's rendering. We do not have, well, except for one exception, 2 exceptions, which I will show you. So this is an artist's rendering of the planet 51 Pegasi b. It is a Jupiter-sized planet orbiting tens of times closer to its parent star than Mercury is to our own sun. It only takes about 3 days for it to orbit its star once. So it's a giant planet orbiting very close. In our own solar system, we have the rocky small things on the inside, and we've got the giant things on the outside, kind of beyond what we call the ice line. So we think of the giant planets as occupying this space in the cold regions of a planetary system, and the terrestrial planets occupying the warm space. And this very first example of a planet we found completely contradicted that paradigm. Huge surprise, okay? Now, this is not the planet we're looking for, right? No solid surface, probably doesn't have life, it's being blowtorched by its parent star, right? So this is not a planet for Goldilocks. Well, what is it that we're looking for? I'll talk about two things, size and temperature, or you could even think of that as size and orbit. And these are typically the kinds of things that we can measure when we find an exoplanet. Size might be in the form of maybe mass, if it's a dynamical detection, maybe radius or brightness. Those are all indications of kind of how big a planet is. Temperature is how close the planet is orbiting to its parent star. So knowing something about the planet's orbit tells you something about the energetics and how much energy, life-enabling energy that planet is receiving, right? So both of those are important if we are looking for life as we know it, right? Life here on Earth is very diverse, but no matter how diverse, how weird, how lurking in some extreme environment it is, every single life form on Earth has one thing in common, and that's that it's carbon-based and uses liquid water as the solvent that facilitates the chemical reactions important for life, right? And so this is why there's so much emphasis on going in search of the water, right? So we are looking for things, for planets that are at the right temperature so that liquid water can pool on the surface, assuming it has a surface. And therein comes the idea of size, right? We want planets that are not so big that the gravitational force is so high that it starts to really efficiently glob on a bunch of hydrogen and helium in the form of molecules and ices that are so common in the universe, hydrogen and helium being the most common elements in the universe, right? So that's what exactly happened to the giant planets. You build up a core, kind of a rocky core, and the idea is that it gets to a certain size and then it becomes very efficient at accreting on these hydrogen and helium volatiles, we call them, and building up an envelope and creating a giant planet, right? No solid surface. By the time you get down to the interesting stuff, the stuff that our cells are made out of, the pressures are too high and it's going to be difficult to form complex molecules, okay? That's the idea. So on the other extreme, down here in the bottom right corner is a little depiction of Mars, probably too small. Well, why do I say that? Well, if you have a very low surface gravity, then you can lose your atmosphere much more easily. And in fact, that's probably exactly what happened to Mars. Mars has evidence of water in its past. This week we learned that it still has something that's kind of like water. We can talk about that at the end if you're interested. But what happens is the sun bombards these planets with radiation, part of which is ultraviolet and X-ray radiation that breaks up water molecules at the top of the atmosphere, right? You break up those water molecules and you've got hydrogen and oxygen gas, and the hydrogen, being the lightest element, is very easy to escape. It escapes easily. And so you literally boil away your hydrogen and you're left with the oxygen that has no more hydrogen to recombine with, and that's how you lose water over time, right? So if the surface gravity of a planet is really low, that process is really efficient. And so although Mars had water probably 3 billion years ago, in fact, oceans of water, today, as you observe, it doesn't, right? So we're looking for kind of that sweet spot, again, for life as we know it, and life that's remotely detectable, not lurking in some subsurface cave. So here's where the Kepler mission comes into play. Kepler, as I said, is a space telescope. It's depicted here, cartooned in the bottom left-hand corner. It has a mirror about 1 meter in diameter, and it's just doing something really, really simple. It's measuring brightnesses of stars with exquisite precision. And it has a wide field camera that's measuring about 190,000 stars simultaneously, taking a brightness measurement of every one of them simultaneously once every 30 minutes, and it did so for 4 years without stopping and without blinking, okay? And the idea is when you build up these brightness measurements as a function of time, and if you observe enough stars, the idea is that some of those planetary systems are going to have orbits that are aligned so that the planet passes directly between the disk of the star and your telescope. The planet casts a shadow out into the galaxy like all planets orbiting stars. And if the the alignment is just right, that shadow will sweep across the face of your telescope, and your telescope will perceive it and measure it as a momentary dimming of light. All right? So that's what you see depicted here with the green trace, is this brightness dimming. How much it dims tells you the size of the occulting disk, or the planet, right? And then you keep measuring, and you wait for it to come around and happen again. Now you've got the time between dimmings, that's the orbital period. Johannes Kepler taught us in the 1600s that the orbital period is directly related to the distance between the star and the planet. So now you know how close to the campfire you are. That is, you know if it's amenable for liquid water to pool on the surface, or if it's in this Goldilocks zone, okay? Just to give you some appreciation for how technically challenging this is, a dimming of light due to an Earth-sized planet orbiting a sun-like star is about 1 part per 10,000 change in brightness, okay? So the analogy I like to make is, imagine the very tallest skyscraper in New York City. It's what, like 80 stories high or something? Maybe it's taller by now, I don't know. Let's say 80 stories high, right? And you're staring at this, it's nighttime, and just imagine that every window is open and every room has a light on, okay? And one person in this building goes to the window and lowers the blinds by about 1 centimeter. That's the change in brightness we have to measure. So that means that we need part per million precision, exquisite stability of our spacecraft and of our instruments in order to see this, okay? But that's the idea. Okay, so I want to give you a bird's eye view of what Kepler has found so far, and I'm doing it with this animated plot that shows the radius of the planet on the y-axis versus the orbital period on the x-axis, the two things that Kepler can measure. So you see points being added to this over time, some blue points and a smattering of pink points. These are all planets that have been discovered over the years from missions or surveys accepting Kepler. Okay, so this is the sum total of all of our knowledge of planets up to the present day. The blue points were discovered with a method called the Doppler wobble method. I can talk about that more if you're interested. The pink points that you see were discovered with this methodology like Kepler's that I told you about. We call that transit photometry because the planet is transiting across the face of the star. And so even with ground-based telescopes, we did start to discover planets with this method around the year, it was 2000, the end of 1999, beginning of 2000 was the first. So if you look at this diagram, you start to see patterns, right? You see a little cluster of pink points on the left, and you see another big swarm of blue points up in the upper right, a smattering of other points. There are some horizontal lines for reference, so you can see where planets of different sizes would lie. And this gives you an impression that in the galaxy, small planets like Earth are actually really rare, right? It also tells you that maybe these very short orbital period giant planets like 51 Peg B might be really common, even though we were very surprised by their existence when they were first discovered. But now I'm going to add to this diagram the planets that Kepler has found over the last, or in its 4-year prime mission. I'll do that with yellow points, and this is what it looks like. You see the really remarkable difference that you can achieve when you put out a new piece of technology, right? We just looked at the galaxy with new eyes, and the veil that was shrouding our eyes to the existence of these small planets was lifted, right? So what we saw before was an observational bias that came about because we didn't have the sensitivity to see them. Now with this detection method we do. Yeah, that's a really good question. Let me repeat it. He said, well, how long do you have to observe before you start to see planets? And is the fact that you have nothing at orbital periods of like 10,000 days because of that finite observing window? And the answer is absolutely. Even now, even though our blinders have been lifted, there are still observational biases in this diagram. All of the absence of planets in this bottom right-hand corner is due to that observational bias. Kepler observed a patch of sky for 4 years. So in order to find an Earth analog orbiting at 365.25 days, you need to see it not just once, but twice, actually 3 times to get a unique determination of its orbital period. So that means you need to observe for at least 3 years in order to see it. Yes?
So your point spread gets markedly thinner above the Neptune line. Is that an observational bias that you guys understand?
Yes, I'm going to show you. Hold that thought, because I'm going to show you something that I'm going to try and convince you that that's not an observational bias. Okay? All right. The other thing I guess I should point out, where does Earth lie in this diagram? Well, it would lie right around here. So that's the sweet spot, right? That's where we're headed. You can see that we do have a smattering of points down there. Those are the hardest planets to find. In fact, if I drew a diagonal that kind of hugged this envelope right here, these are the hardest to find, right, below that diagonal. And so we're just now reaching the nexus where Earth would lie. You can see that NASA does not over-engineer anything. No, we will have another catalog coming out next year, and we might find a smattering of new points in that part of the parameter space, but I think this is more or less what we're going to have to work with. I should also mention that the yellow points that you see here represent over 4,000 planets. 85% of them are smaller than Neptune. In the previous sample from the ground-based observations, 85% were larger than Neptune, so very different. Okay, but Kepler was funded for one very specific thing, to answer a very specific question, and that is, what is the fraction of stars in our galaxy that host potentially habitable Earth-sized planets? The other way to say that is, what is the occurrence rate of small planets in the Goldilocks zone? Okay? So that's what we have to quantify. We will be a failure if we don't calculate those numbers. So in that sense, Kepler is a statistical mission. It's not about finding the one Goldilocks planet. It's about understanding the demographics of planets in our galaxy, okay, of all types. Okay? All right, so this is a histogram of the same distribution. I want to talk a little bit, before I give you the answer to that question that Kepler is working to solve, I want to talk a little bit about the amazing diversity of planets that we've discovered. Here is a histogram of planet size from that sample. And what you see in this diagram is that the most common planet right now known to humanity is a kind of planet we don't even have in our own solar system. Okay? It's these gray, it's literally the gray area in between, right? You've got the rocky, or what we think is rocky stuff down here in brown. You've got the giants over here in blue, and this gray area in between is where we have most of the discoveries, and we don't have any examples of them. What are they? We don't know. And so we look at these, we have started to look at these in some detail. We have follow-up observations of many of them. Here's one example, a planet called Kepler 10c. Kepler 10c is larger than Earth by a factor of 2.35. We've actually also measured its mass with ground-based telescopes, and we find it's 17 times more massive than Earth, as you would expect, right? It's bigger, it's heavier, right? And then we get a density of 7 grams per cubic centimeter. But we've looked at another one, Kepler 138d. It's also bigger by almost a factor of 2, but it has exactly the same mass as Earth. So what this is telling us is that there is a huge diversity of compositions amongst these planets. And by composition, I mean like the recipe for making a planet. How much of the rocky stuff versus how much of the hydrogen-helium stuff you mix in is very diverse. It ranges. It's got a huge range. And so that's really interesting to me. I want to know, is this like something I could stand on? Is this like a big super Earth with more real estate and lots of water, maybe a water world? You know, what are the possibilities? Maybe the water covers the entire planet, but it's not so deep, so you can still have interfaces between water and those other elements that make life. I don't know. So this is just kind of pointing out that there's a lot of possibility to consider. Kepler has also found a class of planets that's orbiting also 10 times closer to its star than Mercury is to our own solar system, but planets that we know are rocky because we've measured their size, their radius, but also their mass. Mass divided by volume is density. This planet, Kepler 10b, we know is a rocky world, but it's being blowtorched by its central star. The star-facing side has an ocean, larger than the Pacific Ocean, but it's an ocean of lava. Because the temperatures on that star-facing side are in excess of that required to melt iron, not just rock, iron, okay? We call these lava worlds. How do we know that it's a lava world? Like I said, we measure the dimming of light, as depicted here on the left. That's real Kepler data. Every white point is a brightness measurement. That tells us the radius. We go to our ground-based telescopes, the Keck 10-meter telescope in particular, and we measured the Doppler wobble. That's what's being depicted on the right. That gives us the mass. Mass divided by volume is density. This cannot be anything else but a rocky planet, okay, with pretty much the same recipe as Earth. Okay?
How do you know it's tidally locked?
Sorry?
How do you know it's tidally locked?
The question is, how do I know it's tidally locked? Because in between transits, in between the dimmings of light, we see the light output from the whole system change by about 2 parts per million and then come back down. What we're seeing is the day side, night side, day side of the planet in its orbit. So I know that there is a huge temperature differential, thousands of degrees, between the day and the night side, and it's consistent, it doesn't change. Yeah. That's a great question. Okay, more extreme. There are planets. Kepler 10b was orbiting its star once every 20 hours. This one, Kick, blah, 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 is orbiting its star once every like 8 hours. It's so hot that it's actually disintegrating before our eyes. Okay, the planet is blowing apart. How do we know that? Well, because when we measure the brightness very precisely as this planet transits the disk, it doesn't have that nice predictable shape because of that comet-like tail. So what you actually see is something like this, right? It takes longer for the brightness to come back up on the right-hand side because the planet has this tail, this cometary tail. I think this is astoundingly interesting because what this tells me is I can actually go to a telescope like Hubble or the James Webb Space Telescope. I can collect light that's filtering through that cometary tail, and it's going to leave fingerprints of what that cometary tail is made out of. That gives me a direct probe into what these planets are actually made out of. Okay, Kepler proved that George Lucas was right, although we got the stars wrong, like wrong sizes. But planets do orbit gravitationally bound stars. So this artist's rendering on the top is the planet Kepler 16b that's orbiting a G-type and a K-type star. G-type stars are these yellow stars. K-type stars are cooler and smaller, and we depict them as being more orange in color. The G-type star would be bigger, so we've got kind of a incorrect size ratio here for these Tatooine stars. But what this tells you is that the planet is orbiting not just one of them, it's orbiting both of them. So you've got not just one star rising in the east and setting in the west, but you've got 2. Moreover, those stars are orbiting one another, gradually changing position in the sky, and they're eclipsing one another. So what we actually observe is very complex and full of information. On the upper swath are the brightness measurements that Kepler takes, okay? And there's some arrows to help your eye. So, for example, we've got blue. If you focus on the blue arrows, That's a really huge dimming of light that happens when one star passes in front of the other star. And then when that star comes back around and passes in front or behind the brighter star, you get the yellow. So you've got blue, yellow, you've got some blues that are missing because the spacecraft went to sleep or something. Blue, yellow, blue, yellow, blue, yellow, red. See, there's a red in there, or a green. The red and the green, those are the planet that's passing in front of the bright star, or alternatively in front of the green star. And it's complicated because these two stars are moving, right? So if you've got one star coming around this way and the planet's coming around this way too, they're moving in tandem, the dimming of light is going to stretch out longer than if the planet happens to be moving around while the other star is moving behind in the opposite direction. Now they're going in opposite directions, and that dimming of light is going to be short. Right? So that's a very rich amount of information from which we can ascertain the masses of the planets and also the masses of the stars involved. Okay, these are Kepler orreries. Many of the stars that Kepler observes have not just one sequence of dimmings of transits, but multiple sequences of transits. So these are multiple planetary systems, and what we have learned is that there is a class or an architecture of planets whereby that's a little bit different than the solar system that we live in. You know that planets in our own solar system orbit in a disk, right? So you can think of that disk as kind of a pancake. These planets that are plotted here for you are dynamically compact systems. These are planets that are orbiting pretty close to one another, so that's why we call them compact. And in these scenarios, the disk is so flat. If our solar system were a pancake, this would be like a crepe. They're exquisitely flat. So it's intrinsically a different architecture than we see in our own solar system, and that's a clue telling us something about how these systems form and how they evolve, okay, how they interact with one another. Okay, and let's see. Finally, the Goldilocks planets. I wanted to say something about which planets, how many of those planets we find are indeed in this Goldilocks zone. So here's another scatter plot. On the y-axis, we have the surface of the central, or the surface temperature of the central star. Right? Remember, stars come in different masses and sizes and luminosities, right? So on the top, we have stars like our sun. These are those K-type stars, and on the bottom, we have the tiny M-type stars, all right? And so the green band is the Goldilocks zone, where the energy you receive on the surface of the planet is amenable for liquid water, okay? So you can see that we have a few dozen that have been discovered so far that are smaller than twice the size of Earth, right? So that's the sample that we're really focusing on. That's the sample that's going to allow us to calculate the fraction of stars in our galaxy that host small, potentially habitable planets. Okay, let's see. I can show you a couple of examples. This is one system, one of those Goldilocks planets, Kepler 186. So you've got a cartoon of the solar system on the bottom that shows the green band where the Goldilocks zone is, right? Kepler 186 is orbiting one of these really low mass stars, what we call an M dwarf. So if you want to be in the Goldilocks zone for an M dwarf, you've got to cozy up next to that star, right? So you see that the green band is really in a much tighter radius, right? So the planet Kepler 186f, which is the Goldilocks planet, is orbiting with a much shorter orbital period. And there are people who argue that that is going to be difficult for life, because when you get planets that are orbiting so close to their star, they can become tidally locked, right? They're more susceptible to the ultraviolet and X-ray emission that's coming off of stars, especially like M stars that emit lots of that kind of radiation. But then in July, we had another exciting announcement. It's now touted as the exoplanet most like Earth, Kepler 452b. So here's a split screen. On the left represents our sun and Earth, and on the right represents Kepler 452b. On the left side of the star, or if you compare these two in the middle there, you can see that the stars themselves are very similar in size. In fact, they're the exact same mass. But Kepler 452 is older. It's probably more like 6 billion years old compared to our sun, which is about 4.5 billion years old. So it's a little older, but otherwise very similar. And they orbit in very similar with very similar periods, Earth at 365 and Kepler 452b at 385. So they're they've got very similar energetics. The strongest difference is that Kepler 452b is 1.6 times the size of the Earth. Is that important for life? I don't know. 1.6 is kind of the dividing line where you start to get big enough that you start to glob on this hydrogen and helium. But the jury is still out. It seems like that's kind of a transition region. So this could be an Earth with more real estate. I don't know, maybe an Earth with even more water. Maybe it's even more amenable to life than our own planet. I don't know. Okay, so now I want to say a little bit about statistics. What is this answer that we're looking for with regards to the fraction of stars that host potentially habitable planets? This yellow cone shows you Kepler's search space. We're searching out about 3,000 light years along the Orion spur, so kind of along a spiral arm, centered on the sun there. And so I'm going to do a little thought experiment. Well, let me first show you this histogram again. You saw this histogram once before. This is just the number of planets in each of these bars represents a different size. Now what I'm going to do is I'm going to try and correct for all of my observational biases in order to transform this into the true fraction of stars that are in the galaxy for these same size bins, okay? And this will speak to the question that we got earlier. Who was it that asked about, are these giant planets really, truly rare? So I do that correction, and I'll just toggle between the two. Whoops. See? That's the bias correction. So the small planets that are really hard to find, I have less sensitivity, so the correction is larger for them. The large planets, though, to hardly change at all. That's because I have 100% completeness. My survey is complete for them. The statistics don't change. So this scale tells you that the frequency of giant planets like Jupiter in these warm interiors of planetary systems are an order of magnitude smaller than for the Earth-sized planets. So this tells us that small planets, at least orbiting within an Earth-like orbit, are much more common than Neptune's and giant planets. Okay, so what does that translate to? Well, I'm going to ask the question, given these statistics, where is the nearest potentially habitable Earth-sized planet? How far out do I have to go to find one, right? So here's the Milky Way galaxy, a cartoon of it depicted from the top down. And what I'm going to do is I'm going to scale the continental United States to that size, okay? And here we are on the shore of the Pacific, and you're turning east, and let's look across the continental United States and ask ourselves, where is the nearest potentially habitable exoplanet likely to be? And the answer is right about there at the tennis courts. It's very close. The answer is 3 parsecs, or about 10 light years, with 95% confidence. Okay? So this makes the galaxy seem like a smaller place, don't you think? This makes the idea of actually going and visiting these places a little more tangible, right? It makes the search for life seem all the more feasible, right? And in fact, we know how to do this. We know what to do. We know what technology milestones have to be met in order to do this within the next 30 years, even, to look at these planets and look for indications of life. Okay, another way just to drive this point home, I don't know if you can see it, but in this little yellow bullseye in the very center, there's a red dot. Do you see it? All right, that red dot is about 10 parsecs, or about 33 light years in radius. This is a 3D animation of the stars within that radius, 10 parsecs, okay? There are about 350 stars in like 250 stellar systems, 200 some odd, 250 plus. 240 of them are like these M-type stars, these cool M-type stars. About 20 are stars like our own sun. Those are colored yellow. The M dwarfs are colored red. Like I said, that's 10 parsecs, or 33 light years. That's a factor of 3 larger than the distance I just gave you of 10 light years, right? So volume scales as r cubed. That's a factor of 27 in volume, right? So if there's one planet, at least within 10 light years, there's 27 times that in this tiny little volume that was just that little red dot. So these are the stars that we want to target. This is what we want to explore. I would argue we want to go out about another factor of 3 in diameter, because I want more yellow points. I want more stars like our own sun to probe. And there is where we're going to focus our search for life. And let me just highlight, we're kind of done working up to the present. And now for the remainder of talk, I want to tell you a little bit about my dream for the future. But let's just reflect here. I mean, all of this has come about, and this search for life has become kind of within our grasp just over the last 20 years. Between 51 Peg B and Kepler 452b, we have grown orders of magnitude in orbital period, mass, radius, radiation, energy, all of these parameters. We've gotten very close to finding true Goldilocks planets. So now the task at hand is to move from finding planets in the habitable zone to finding habitable environments, right? To find truly habitable environments, and that will occupy us over this next 20 years. So let me say a little bit about that future search. This is NASA's portfolio, just one government agency's portfolio. Kepler, you can see, is here kind of in the middle. We've got 2 missions that I'll talk about together, TESS and JWST, very briefly. In the upper right is a mission called WFIRST, which I think I'll skip over a little bit. It's another demographics mission. It's going to speak to the demographics of planets not within an Earth orbit, but beyond an Earth orbit. So after that mission, we will have a complete census of planets in the galaxy. Not a census, but demographics, right? A representative sample. And then I will end by talking about what's listed here as a notional mission, and we're calling the New Worlds Telescope. This is the what is being studied, will be studied over the next 5 years as we develop mission concepts. Okay, but first, TESS and JWST. Just to remind you, this is Kepler's search space, that yellow cone of light that goes off into the spiral arm of the galaxy, looking out 3,000 light years, but at one patch of sky, without blinking. 0.25% of the whole angular area of the sky, right? Just one swath. TESS is a mission very much like Kepler. It's going to do transit photometry, but it's going to survey the entire sky out to like 200 light years. So it's going to look everywhere. It's going to have to do that with a step and stare approach. It can't stay fixed at one spot at a time. It's going to have to move around. That means that it will only catch, planets with orbital periods of like 80 days and less. So short period things, but they'll be nearby. And the reason this is interesting is because these nearby stars will be amenable to characterization studies afterwards with the James Webb Space Telescope. The James Webb Space Telescope is the successor to the Hubble Space Telescope. It launches in 2018. And the James Webb Space Telescope will be capable of determining what's in the atmosphere of some of these planets. So here's the idea. This is the planet Venus transiting in front of our sun. Okay? If you look carefully, you can see a very thin yellow line that hugs the planet. Can you see that? Especially where you have contrast in the upper left-hand corner against the black background. That's the atmosphere. Very tiny, thin atmosphere. The scale height is like 5 kilometers. The total area that atmosphere intercepts is like 1/200th the area of the disk of the planet itself. Okay, it's very, very thin. But what James Webb will try to do with the transiting planets that TESS finds is it will observe the planet when it's in front of the star. It will see the starlight filtering through that very thin haze of an atmosphere. That atmosphere will leave a fingerprint upon the light that the James Webb Telescope will catch. It will spread that light out into a spectrum and look for the chemical fingerprints of what the atmosphere is actually made out of. Okay? And here's a cartoon illustrating an example of that. The James Webb Space Telescope will do this in spades for the sub-Neptune super-Earths, those planets in the gray area that we don't know anything about. It's going to knock that out of the park. We're going to know all about those planets. We're going to know what their atmospheres are made out of. It's going to be great. I don't suspect that James Webb is going to be able to do this without a huge investment in resources for the Goldilocks planets that are really tiny. For that, we need a different methodology. The planets are just too small. The atmospheres are too thin. We just don't have enough photons to be able to see the signatures. Okay, so for that we're going to need something different. And imagine, just think, okay, here you're getting fingerprint from the photons that happen to pass through this tiny little narrow strip. What if I could get all the photons that are bouncing off the whole surface, right? Like reflecting off of the whole entire surface. That's a much bigger area, right? That's just, in theory, has to be easier, right? And indeed it is, if you can take an image of a planet. But you have to be able to take a picture of a planet, right? This is tremendously difficult. So now let me talk about the New Worlds Telescope, because that is the objective of the New Worlds Telescope. Here's the technical issue, okay? Trying to find a planet orbiting a star, like taking a picture of it, is like trying to see a gnat next to a searchlight. Right? The glare of the searchlight, or the star in this case, is 10 billion times the light that's coming off the surface of the planet. So these planets are literally lost in the glare. In order to accomplish this, we have to block out the glare of the star. It's analogous to going outside on a starry night. You walk out, you want to look up at the sky, like maybe when you guys saw the eclipse the other night. And you look up in the sky and you see nothing, right? Because you've got all these bright street lights in front of you. All you have to do is put your hand in front of the street light. Your pupils dilate out and you can see the stars, right? So you just block out the light source and then you can see what's behind it. That's what we're trying to do. There are 2 ways of doing this, and we're doing technology development on both right now, and we've made a lot of progress. So I'm going to show you 2 videos that illustrate the technology. Okay? The first one has audio, so I assume that the audio is working. So I'm going to go ahead and start that. If I can find the cursor. Here it is.
A distant star is orbited by 2 planets. One looks similar to the Earth, the other is a gas giant. When viewed from a distance, the 2 planets disappear into the glare of their sun. How could we ever find these planets all the way from the Earth? By using a space telescope with a coronagraph to separate starlight from planet light. As the star's light passes through the telescope's large mirrors, it picks up small distortions. Diffraction adds concentric rings to the image we see. To reveal the planets, first a coronagraph uses a mask to block much of the star's light and redirect the remaining light to the outer edges. A washer-shaped device can now block most of the rest of the star's light. Because the planet's light comes in at an angle, it misses the mask and passes through the center of the washer. But when we turn up the image signal by collecting more light, we can see that the planets are still hidden under blobs of leftover starlight. To remove these blobs, the coronagraph has a special deformable mirror that can change shape by using hundreds of tiny pistons. This can correct distortions in the light beam. As the mirror deforms, the blobs of light as seen in the monitor slowly begin disappearing, finally revealing the brighter of the two planets. Afterwards, the fainter planet also comes into view. We can now see objects more than 1 billion times fainter than the star. And if the light from these planets is passed through a prism, we can spread it out into rainbows of color. But some colors are missing. They were absorbed by gases in each planet's atmosphere, giving us important clues about their composition. The search for life in the universe has taken a new step forward.
I never get tired of seeing that. It gives me goosebumps. Okay, so that's coronography, a coronagraph, where you put something in the light path to block out, just like your thumb, block out the light. The problem is that stars create this diffraction when they come into your telescope, and you saw that, right? Now, there are technology hurdles to accomplishing this. One, for example, during that process where you've got the pistons and you're adjusting the shape of the mirror and making all of these subtle corrections, during that process, you need pointing stability down to like a picometer. I mean, really, really exceptional pointing stability. So that's one technology hurdle. Another technology hurdle is that, well, okay, fine, but you still need to collect enough photons, right? These things are really, really dim. I need a huge photon bucket, which means a big, gigantic mirror, right? The only way we're going to get a big, gigantic 10-meter dish mirror out into space is by making it segmented and folding it up into your rocket fairing, right? The problem is that when you do that, when you make a segmented mirror, all of that diffraction that you saw that makes the rings is different. So we have to learn how to do this with segmented mirrors. We have to learn how to achieve that picometer stability in the pointing, in the thermal sensitivity, all of that. It's really going to be challenging. Now, you can simplify that if you figure out a way to hold a giant thumb out into space instead of putting it in your optical path. Okay, if I can put a giant thumb out in space, it's going to make it much more simple. I'm taking it out of the optical path, and I don't have to worry about that wavefront control. And we're trying that. This is called star shade technology, and this is the next video. Here there's no audio. What you're seeing is a probe class star shade that is unfurling and creating a shape that looks like a sunflower. It has that special sunflower shape because of the way that we want it to control diffraction. But the idea is that you're going to fly this thing independently some tens of thousands of kilometers away so that it gets really tiny and perfectly blocks out the starlight. You're going to have another space telescope that is doing telemetry or metrology to communicate with the star shade and get it perfectly pointed and aligned and hold it there steady like a giant thumb up in space so that you can see the planets that are lost in the glare, okay? Two different technologies. They each have their advantages and disadvantages. The disadvantage of this one, although it made the optics really simpler, much more simple, the problem is that it's tens of thousands of kilometers away, and now you want to point over there and look for a planet over there, and you've got to sit there and wait while the star shade makes the journey from one place to another. Right? So you lose a lot of time. But if the telescope can stay observing something else, making other astrophysics contributions while you're waiting for that slew time, maybe that's something worth doing. So those are the two technologies. I wanted to show you that indeed we've already done this from the ground, albeit not for small Earth-sized planets in the Goldilocks zone. There was an announcement just about a month ago, the first planet discovered by an instrument called the Gemini Planet Imager. GPI. The Gemini Planet Imager, here is the image from that telescope. You see the concentric rings. That's the airy pattern due to the diffraction, just the remnant airy pattern. But here's the planet, 51 Airy B. This was another system, I can't remember which instrument discovered it, I think Keck. And here you see 1, 2, 3 planets, but what you also see, because we've been observing this for so long, is you see the planets actually moving in their orbits. Now you've got some dynamical information to tell you something about the masses of these planets. So this is really promising, right? This looks great, but just one caveat that what you're seeing there are planets larger than Jupiter, younger than Jupiter, so they're hotter than Jupiter, and they're orbiting tens of times further out than Jupiter. So here is what our own solar system would look like with such an instrument, actually a better instrument. And, you know, Jupiter and Saturn, okay, that's pretty much, we can do that. What we want to achieve, though, is find the Earths that are in this annulus. Right? So that's why it requires a space-based telescope to get above the atmosphere. It also requires a very large light bucket because these things are going to be faint. And so this is what we're talking about. Okay? We've got the Hubble down here, dwarfed in the lower left-hand corner, the Hubble 2.4 meter telescope next to Goldilocks there. James Webb, its successor, at 6.5 meters in diameter. But what we're proposing, our moonshot right now, is a 10 to 12 meter class telescope that will have the capability of seeing this tiny annulus and collecting enough photons so that we can search for biomarkers.
How cheaply can you actually build a telescope like that?
What's that?
How cheaply can you actually build a telescope like that?
How cheaply can you build it? The good news is that the cost per unit collecting area of telescopes is going down. So they do get cheaper as you learn more and as you build them, but they're still extraordinarily expensive. So if I were to project out a couple of decades as to when we would start to build this thing, I could posit a guess that it would cost about the same as the James Webb telescope does now, something on the order of $5 to $10 billion. Yeah. I'm sorry, did I shock you there? Come on, this is Google. Okay, let's see. Why such a large telescope? I can answer those questions if you're interested. Just to say that what we really want to do, as you saw in the video, is take a spectrum and look for the presence of all of those gases that are emitted by complex life forms on planet Earth as they metabolize food into energy, things like methane, oxygen, respiration processes, all of those things that are indication, not just a planet, but of an actual living world. Again, this is possible. It's not limited by what we know. It's not limited by technology. It's just simply limited by resources. So with enough time, we will accomplish this. Could be maybe not in my lifetime, but certainly in my children or grandchildren's lifetime. I think that this is going to happen, where one day soon we will know for certain that life does or does not exist beyond Earth. So that's where we're headed. And I'll end with the beautiful retro travel posters that JPL created for these worlds of our imagination that actually do exist, just with quite not so much color yet. All right, thank you very much. I'd be happy to take questions.
I recently read that you should be able to detect the glare of a water-covered planet going in front of the star that they orbit around. Would Kepler be able to see this, or any of the satellites that are proposed?
So to detect the glare, so when you say glare, to me you're implying reflected light. Mm-hmm. So light that's coming from the star is bouncing off of a shiny surface, mm-hmm. right? And we see that. And so the question is that possible with Kepler? We do see some phase functions as planets are orbiting around. the kind of specular reflection that you're talking about would happen at precise moments. We see these kinds of phase functions for mostly giant planets that are heated on one side compared to the other. So I don't know, I'm not aware of any such a detection. We will do this in the future. I think that our best bet is to do the transmission spectroscopy between TESS and JWST, see the light come through the atmosphere. So you're not talking about a glare, you're talking about transmission, and hopefully see evidence of water vapor. Whether or not we'll have the kind of situation, I'm not even sure water worlds exist in entirety, but certainly oceans. The kind of specular reflection that happens quickly when you're just at the right angle, I think, is going to be very difficult to find. Yeah, just thinking out loud here.
Direct imaging, is it easier to just to do the reflected light from the star, or the transmission from the planet based on its temperature?
Okay, so the direct imaging missions are reflected light off of the surface, but they can also be, and this is where I thought you were going with that question, they can also be thermal emission, like that is, the warmth of the planet itself, like in the case of the multi-planet system from direct imaging that you saw, that was enabled by the fact that the planets are young and hot, so they're emitting thermal radiation, and you're seeing that emission as well.
Well, and the contrast between the star and the planet would vary based on which wavelength you're looking
Absolutely,
at. Absolutely, that's
right.
Too.
That's
so
correct.
If it would be easier to look for really hot planets close in because they're emitting a radiation length that the star doesn't emit at as much as it normally.
Yeah, but see, when they're close in, you have a resolution problem. One of the other reasons why you need a big telescope, even to see the Goldilocks zone, is because you're trying to be able to resolve a planet next to a star, right? And so resolution is proportional to the diameter of the telescope. So the closer in you want to see, the higher resolution you're going to need, and we're already really hard-pressed to do that for an Earth out at 365 days. So if you want to do something for planets that are even closer, you have two choices. Either you do transmission spectroscopy in the way that you've mentioned, but that, of course, only works if you have the right geometry, right? Or the other alternative, and I think this is going to happen, on the ground, we are already building 30-meter telescopes. So telescopes that are 3 times bigger in diameter, 27 times more collecting area, and you get the same benefit with resolution. So now you have the possibility of seeing the habitable zone of the M-type stars, which are closer in. You can't do that with a 10-meter class telescope even in space because you just don't have the resolution. But with the 30-meter telescopes from the ground, if we can work out the rest of the technology challenges, we might be able to do it.
You mentioned the orientation. Do you find that it's typically consistent, that we tend to be with the disk of the galaxy, or are they pretty randomly oriented?
Yeah, that's a really good question. The question is, do we have any preferential geometry in the galaxy with these orbital planes? And the answer is no, that they're all cattywampus, randomly distributed.
Would there be any disadvantage or advantage or disadvantage to a telescope based on the moon, so you have something solid to put it on and still no atmosphere?
Is there an advantage to building a telescope on the moon?
I'm thinking, like, instead of having to put a satellite out, far away, you might be able to put a relatively small thing on a mountain, a few kilometers away.
Which is kind of what we're doing on the Earth to test the technology. We're going out into the desert and setting up systems like that. I don't know. That's a really good question. There are other challenges you have to think about when you go to the moon. First of all, getting supplies there, of course, because you're going to have to make multiple trips. But also the dynamics on the moon, you've got a lot of dust, right? And so I know that one of the biggest technological hurdles to building telescopes on the moon is just the amount of dust. And we've got the regolith, which has this very fine dust. In fact, if you do hiking in California, because of the drought, the ground, God, I hiked up the ridgeline the other day for the eclipse, and it was like I was walking on the moon. It was like poof, poof. So if you have even lower surface gravity, that dust is going to loft. It's going to get into your electronics. It's going to be a mess. So, yeah, nobody seems to be thinking seriously about that, but that doesn't mean that it's...
What's the status of Kepler today? I know that with its reaction wheels failing, that there was some backup plan in mind.
Yeah, thanks for asking that. Maybe I'll go ahead and back up a little bit. So the question is, what is the status of Kepler today? a few years ago, sorry, this is not very efficient, is it? Well, several years ago, Kepler lost one of its reaction wheels. And so the reaction wheels are these like gyroscope things that there are 3 of them, one for each axis, and they keep the telescope pointing very stably, right? So there was some redundancy built into the spacecraft. There were 4. You only need 3 because there's 3 axes you can rotate about, right? And so we had 4. We had some redundancy. We lost 1. No problem. We've got 3. But then a couple years ago, in fact, it was on my birthday. I was just about sitting at my birthday lunch, and I got the phone call. We lost a second reaction wheel. So now we were down to 2. That meant Kepler was spinning about one axis. We had no control, okay? So, for me, I was like, well, okay, we already completed our baseline mission. We'd already collected 4 years of data, and that was our baseline mission, so I'm good. But it was a disappointment. But the engineers at Ball Aerospace were very clever. And what they did was they recognized that there is an axis of symmetry built into the spacecraft itself. And so, well, let me back up for a second. What is it out in space that makes the telescope spin? And the answer is radiation pressure from the sun. So you're literally being pushed on by light. Okay, it's very small, but it accumulates, right? So they recognized that they could utilize this axis of symmetry if they lined it up with the vector pointing towards the radiation pressure or towards the sun, and they did that perfectly. It would be like pointing a boat directly upstream. If you balanced it, you would neither yaw to the right nor to the left. You would stay the course. And that's what they did. So that axis of symmetry happens to be in an orientation that puts the telescope observing along the ecliptic plane of the solar system. So it limited the amount of places where we could point and observe. It also meant that we could not point the telescope to the baseline patch of sky that we were observing. But it actually opened up the possibility of this whole entire new thing called K2, which is Kepler's second mission, but actually named after the mountain, K2. Mm-hmm. And so K2 is looking at these patches of sky along the ecliptic, and you see it there traced out as this sine wave with regards to the plane of the galaxy, which you see there as a flat image across the screen. So it's going to observe each of these patches of sky. It's been doing that already for over a year now with great success. So it's kind of like a step and stare approach, more like TESS, right? And we're finding lots of planets in these patches, including some planets that are, that pink part just shows you kind of where in the sky we get to look relative to the Kepler field of view during the baseline mission. When you add up all the fields that we will observe over a few years, maybe 4 years, that adds up to about 4% of the sky instead of 0.25%. So it's great, and we're finding planets that are actually really close by, like this 3-planet system that's just 100 light years away. So it's doing good stuff, and I think it's actually going to find some really good candidates for the James Webb Space Telescope to observe when it launches in 2018.
How long is the mission expected to continue?
How long is it expected to last? So there is a hard constraint, and that's the fuel. There's a fuel on board the spacecraft that does some thruster firings to change position, and that does have a finite lifetime, but I think it'll easily last 4 years in this configuration.
So this is obviously a lot of data you guys have collected.
How much data is left to be analyzed? We're still actually even working on the data from the baseline mission, that first 4 years between 2009 and 2013, because we're improving the pipeline that does the analysis. So we'll get some more discoveries from that data, but we're wrapping that up. That's due to finish by September of 2017. So we've got about a little less than 2 years to finish up the analysis of that data. That said, the data sits in the public archives, and scientists will be analyzing that data for decades to come because it's such a rich data set, right? Kepler's level 1 science requirement is just to compute the fraction of stars with planets of certain properties, but there's a lot of other things you can do with this data to characterize planets and learn about different architectures and oddball cases and all kinds of things, right?
What is the process for scientists to get access to that?
I'm sorry?
What is the process by which scientists get access to
Oh,
that?
you could do it right now with your phone. It's there. It's at the NASA Exoplanet Archive. Is one repository, and then the Multi-Mission Archive at the Space Telescope Science Institute is another archive. So yeah, it's all publicly available. Anybody can play with it. Yeah. Well, thank you very much for your time. Any other questions?